In this session we do the reverse direction in this if and only if proof. So we've just done, just finished at the end of the previous session the if part. So that boils down to if Q then P. In other words, you accept the right hand side and you have to prove the mathematical statement P on the left hand side. And now we do the only if part, that's the other way around. So only if, in other words, P only if Q, and that translates as usual into the if then form as if P is true then Q is true. So P arrow Q. In other words, accept the left hand side and prove the right hand side. Okay, so what does that mean? So P, going back to previous session, what's statement P? P is a language is Turing recognizable. Language is Turing recognizable. Now what does that mean? It means that there's a Turing machine, standard Turing machine M, that recognizes the language, which means every string in that language is accepted by the machine M, and any other string is rejected. Right, and you have to show, now given that that's true, then you have to show that Q, and what's that? That statement is that language is enumerated by an enumerator. So in other words, there's a machine E, a new enumerator. In other words, it'll for every string that's accepted by your M, by the Turing machine, the standard Turing machine, that string, that same string, will appear on the list, printed out. It'll be printed by the printer. That's what enumerators do. Okay. So yeah, you have to show that that's the case, right? Now how to do that? Let's see. So we're going to, it'll be a proof by construction. Well, in a sense on paper, we will construct an enumerator, an E, machine E, for the same language, A, that's recognized by the standard Turing machine, M. Okay, how to do that? Well, the proof given by Sipser still, I feel, glosses over details still. Anyway, I hope you can follow the following, because there's still quite a bit between the lines. So, the strategy is just generate effectively all possible strings. So assuming a given string alphabet, okay, capital sigma. So that's assumed given. And then generate all, so sigma star, generate all possible strings from that alphabet. Starting with just one character, one symbol, well, in fact, probably starting with the empty symbol, epsilon. And then all possible strings with just one symbol in them. So if this alphabet here has, let's say, big N symbols, so your first N different strings would be just those N one symbol strings, strings consisting of just one symbol. And then all possible strings with two symbols, so you'd have N squared of those. And all possible strings with three symbols, so you'd have N cube of those, and so on. Right? So you just generate all all possible strings, and so these S1, S2, what are they? Well, they're just the strings. So your first string, second string, and so on. So all these S's, that's a list of all possible, infinite, right? But countably infinite strings in your sigma star. Okay. Now, so we're given a list of all these possible strings. All strings with just one character, one symbol in them, all strings with two symbols in them, and so on. Okay, so S1, S2, dot, 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 infinitely, countably infinitely. Right, so that's preliminary. Now, so we have to, we're given a standard machine M, and we've got to find an equivalent machine E, an enumerator that prints out all those accepted strings. By if the machine M, the standard Turing machine, if it accepts a string, of all these, then you want the E, the enumerator, to print it out. Okay, they're to be equivalent. So how to do that? How can we how can we construct a machine E, an enumerator, to ensure that it will print out a string if it is accepted by M, the Turing machine, standard Turing machine? So how to do that? Well, here's one way. Well, firstly, just ignore the input. You may ask why. Well, it'll become clear in a minute. Okay. Now, go through the following loop. You start with I is 1, and what does I mean? Well, for the moment it's just a counter. Okay. You do it for I is 1, and then you do it for I is 2. So you have this sort of loop of loops, and then you do it for I is 3, and so on. And then, given this integer I, positive integer, you run your machine M, your standard Turing machine, for I steps. Okay. Now it's a Turing machine, so the moment the Turing machine lands in an accept state, it stops. Right. So you can't run it for more steps than the number of steps it used to get to an accept state, right? Because it stops after that. You can't run it beyond that. Okay, so we run this machine for I steps, right? On each of these strings, and you'll have I of them. So choose an I, and you'll start I systematically at 1, and then 2, and 3, it just keeps going. And you run your machine for I steps on these first I strings. Okay, generated systematically from this. Well, this is from your string symbol alphabet. Alright, so you run the machine for I steps on each of these. Now, if any of these accept on the I step, right? It's got to be that way. Then you have the machine E. Will print out that. Let's say there's some string in here, call it SJ, that the Turing machine M accepts. Will then print it out. So design your E so that it does that. It prints it out when your M. So in effect you're getting your E to simulate J. Like it's, in a sense, it's got a sorry, I'm not doing that. To simulate your machine M. It's as though the numerator has a Turing machine M inside it, so to speak. Right. Okay. So if one of these, say SJ, accepts by the Turing machine M, well, print it out. Okay. Right. And now, so if M does accept some particular string, call it S, it'll eventually appear on the printed list. It'll be printed out by E. Okay. In fact, if you think about it, think it through, that particular string will probably get printed out an infinite number of times. Why? Because the machine M is going through this list an infinite number of times. Right? It starts here and goes up to I, but I is increasing all the time. So it's going through these earlier ones, you know, again and again and again and again. So it'll probably, if one is found SJ, it'll probably be printed out, you know, an infinite number of times. Okay. And a comment here before we get into the next topic. So doing this kind of thing, it's effectively it's running the machine M in parallel on all possible input strings, which is, you know, you can look on it that way. All right. So next topic. I'll switch around. Now, you may remember the very title of this whole chapter, you know, chapter 3, is the ChurchTuringThesis. Statement or belief, or well, it's usually just called the thesis. Something you suspect to be true. You suspect strongly that it's true. You may not have rigorous proof that it's true, but you, like in a sense, you think the sun's going to come up every day. You don't have any proof that it will be. If you've done any philosophy and you've read Hume, H-U-M-E, you'll realise, you know, you can't prove a thing like that. But you know, people believe it. So the ChurchTuringThesis, which we still haven't really formally specified, you know, what is that thesis? But we're heading towards it. So now, yeah, we're getting towards the end of the chapter. Finally, we're getting, having discussed now quite a few variations of Turing machine designs. So we've just done our, what, third one, is it? So what have we done so far? The multi-tape version, or variant, the non-deterministic variant, this one.